Hello everyone, welcome back to my YouTube channel. Myself Monisha V from 3rd year ISC department studying in Sri Venkateshwara College of Engineering. My topic for today is AVL tree, which is also known as Adelson-Welsky and Landis. So these are the contents for today's topic. 4 rotations in AVL tree and operations on AVL tree. Let us move towards the introduction part. AVL tree full form is Adelson, Welsky and Landis. In 1962, GM Adelson, Welsky and EM Landis created the AVL tree. To honor the people who created it, the tree is known as AVL. The AVL tree is a height balanced tree where each node's right and left subtree height differences are either -1, 0 or 1. A component known as the balance factor keeps the subtrees height differences apart. As a result, we can define AVL as a balanced binary search tree in which each node's balance factor is either -1, 0 or +1. In this case, we can use the formula to determine the balancing factor. Balance factor equals height of left subtree minus height of right subtree. So now let us know the advantages of AVL tree. AVL trees were developed to overcome the dependency of operations on the height of the binary search tree and the inability to control the tree's height. Hence, the main advantage of AVL tree include it can be used to perform searching operations on dynamic data sets just like binary search tree. Its height is always balanced, that is, it always stays as a balanced BST where n is the total number of nodes present in the tree. It has a self-balancing property which is implemented by calculating the balance factor of all the nodes after each operation and performing certain tree rotation to make sure that all the nodes follow the AVL balancing criteria. So there are 4 rotations and they are further classified into 2 types. So as you can see in the diagram, the rotations are divided into single rotation and double rotation, where single rotations are further divided into left rotation and right rotation, and double rotation is further divided into left right rotation and right left rotation. There are basically 4 types of rotations which are as follows. LL rotation, which are inserted node in the left subtree of left subtree of a. RR rotation, inserted node is in the right subtree of right subtree of A. LR rotation, inserted node is in the right subtree of left subtree of A. RL rotation, inserted node is in the left subtree of right subtree of A, where node A is the node whose balance factor is other than -1, 0 or 1. So let us know the example for AVL tree. So as you can see in the diagram, this is the example for AVL tree where the root node will be 25 and the lesser node will be in the left node and the greater node will be on the right node. The above tree is a binary search tree and every node is satisfying balance factor condition. So this tree is said to be an AVL tree. AVL tree rotations. In AVL tree, after performing operations like insertion and deletion, we need to check the balance factor of every node in the tree. If every node satisfies the balance factor condition, then we conclude the operation, otherwise we must make it balanced. Whenever the tree becomes imbalanced due to any operation, we use rotation operation to make the tree balanced. Rotation operations are used to make the tree balanced. Rotation is the process of moving nodes either to left or to right to make the tree balanced. So the first one will be the single left rotation, which is also known as LL rotation. In LL rotation, every node moves one position to left from the current position. To understand LL rotation, let us consider the following insertion operation in AVL tree. So as you can see in the diagram, in the first tree, the tree is imbalanced. To make the tree balanced, we use the LL rotation, which moves node 1 position to the left. After the LL rotation, the tree will get balanced. Second one will be the single right rotation, which is also known as RR rotation. In RR rotation, every node moves one position to right from the current position. To understand RR rotation, let us consider the following insertion operation in AVL tree. So as you can see in the diagram, the tree is imbalanced because node 3 has balance factor 2. To make the tree balance, we use the RR rotation, which moves node 1 position to the right. After the RR rotation, the tree will get balanced. Third one will be the left-right rotation, which is also known as LR rotation. The LR rotation is a sequence of single left rotation followed by a single right rotation. In LR rotation, at first every node moves one position to the left and one position to the right from the current position. To understand the LR rotation, let us consider the following insertion operation in the AVL tree. So as you can see in the diagram, in the first tree, the tree is imbalanced because node 3 has balance factor 2. In the second tree, we are doing LL rotation. So after doing the LL rotation, it is been passed to the RR rotation. So after completing the RR rotation, the LR after RR rotation, the tree will get balanced. Right-left rotation, which is also known as RL rotation. The RL rotation is a sequence of single right rotation followed by single left rotation. In RL rotation, at every node moves one position to right and one position to left from the current position. To understand RL rotation, let us consider the following insertion operation in AVL tree. So as you can see in the diagram, the first tree is imbalanced because node 1 has a balance factor of -2. So let us move towards the next step, that will be the RR rotation. So the after RR rotation, the tree will pass to the LL rotation. So after doing the left rotation, the tree will get balanced. Operations on an AVL tree. The following operations are performed on AVL tree are search operation, insertion operation and deletion operation. Search operation in an AVL tree. In an AVL tree, the search operation is performed with O, that is log n, time complexity. The search operation in the AVL tree is similar to the search operation in a binary search tree. We use the following steps to search an element in AVL tree. Step 1. So these are the 9 steps to search the element. So step 1 will be read the search element from the user. Step 2. Compare the search element with the value of root node in the tree. Step 3. If both are matched, then display given node is found and terminate the function. Step 4. If both are not matched, then check whether search element is smaller or larger than that node value. Step 5. If search element is smaller, then continue the search process in left subtree. Step 6. If search tree is larger, then continue the search process in the right subtree. Step 7. Repeat the same until we find the exact element or until the search element is compared with the leaf node. Step 8. If we reach to the node having the value equal to the search value, then display element is found and terminate the function. Step 9. If we reach to the leaf node and if it is also not matched with the search element, then display element is not found and terminate the function. Insertion operation in an AVL tree. In an AVL tree, the insertion operation is performed with O log n time complexity. In AVL tree, a new node is always inserted as a leaf node. The insertion operation is performed as follows. Step 1. Insert the new element into the tree using binary search tree insertion logic. After insertion, check the balance factor of every node. Step 3. If the balance factor of every node is 0 or 1 or minus 1, then go for the next operation. If the balance factor of any node is other than 0 or 1 or minus 1, then the tree is said to be imbalanced. In this case, perform suitable rotation to make it balanced and go for next operation. So, for the example for the insertion, let us construct an AVL tree by inserting numbers from 1 to 8. So as you can see the example, by inserting 1, the tree is still balanced. By inserting 2 to the 1, tree is balanced. By inserting 3, the tree will get imbalanced. So we need to do the LL rotation. So after the LL rotation, the tree will get balanced. Insert 4, the tree is balanced. Insert 5, the tree is imbalanced. So let us do the LL rotation at 3. So after the LL rotation, the tree will get balanced. In the step 6, when we insert 6, the tree is imbalanced, becomes a right child of 2. So the we need to do the LL rotation at 2. So after the LL rotation, the tree is balanced. Insert 7, the tree will get imbalanced. Do the LL rotation at 5. So after the LL rotation, the tree will get balanced. Insert 8, the tree is balanced. So this is the example for inserting numbers in an AVL tree. So deletion operation in an AVL tree. The deletion operation in an AVL tree is similar to deletion operation in BST, but after every deletion operation, we need to check with the balance factor condition. If the tree is balanced after deletion, go for next operation. Otherwise, perform suitable rotation to make the tree balanced. The algorithm steps of deletion operation in an AVL tree are: locate the node to be deleted. If the node does not have any child, then remove the node. If the node has one child node, replace the content of the deletion node with the child node and remove the node. If the node has two children nodes, find the in-order successor node K which has no child node and replace the contents of the deletion node with the K, following by removing the node. Update the balance factor of the AVL tree. So this is the algorithm for deletion operation. For better understanding, let us consider an example where we wish to delete the element having value 10 from the AVL tree created using the element 10, 20, 30 and 40. The below GIF demonstrate how we can delete an element from an AVL tree. So this is the diagram for this is the example for deleting an element from an AVL tree. As you can see, they have given the AVL tree. So by deleting the element 10 by the direct removal, the leaf node of 20 the 10 will be removed. So the resulting tree will be shown. So it will be imbalanced. So by doing the RR rotation, the tree will get balanced, as you can see in the diagram. So the conclusion for today's topic. AVL tree is a height balanced BST that maintains its height by performing tree rotations according to a balance criteria. Balance criteria for all nodes, the subtree's height differences should be at most 1. AVL tree height is always O log n, that is, it has a logarithm time complexity for all the operations. Tree rotations are changes in the structure of the tree done only on 3 nodes without affecting the elements order. All AVL tree operations are similar to BST except insertion and deletion. When n is large, AVL provides faster and reliable search operation than BST. Thank you.